Have you ever really stopped to think about what's going on inside your body when you, I don't know, decide to move? I mean, from lifting something heavy to just cracking a smile, there's this unbelievable microscopic process powering every single thing you do. So what we're going to do is zoom way in, way past what you can see, and check out the incredible molecular world that makes it all possible.
And this quote, it just nails it, doesn't it? Whether you're doing a huge, powerful jump or something as simple as a smile, it's all powered by the exact same incredible biological machinery. Every single movement, big or small, they're all connected right down at the molecular level.
Okay, so first up, let's start this journey. We're going deep inside our own muscles to see this miracle of movement for ourselves.
You know, the best way to really get a handle on this whole process is to think of it like a play. And of course, every play needs its cast of characters, right? Well, in our case, the stars of the show are a team of very specialized proteins.
All right, so let's meet our two main stars, actin and myosin. These two are the heavy lifters, the real workhorses. A good way to picture it is to think of actin as the track, or the road, and myosin, well, myosin is the motor that actually moves along that track. That's what creates the force for contraction. They're the ones literally doing the work.
But, you can't just have these motors running all the time, right? That would be total chaos. And that's exactly where troponin and tropomyosin come into the picture. These two, they're the regulators, the gatekeepers. Their whole job is to control when actin and myosin are even allowed to interact. They're pretty much the stage managers of this whole show.
So here's the whole setup in a nutshell. On one side, you've got your actors. That's actin and myosin, the ones actually performing the movement. And on the other side, you have the regulators, troponin and tropomyosin, who are directing the whole thing. It's a really elegant, perfectly balanced system.
Okay, so we've got our actors and we've got our directors. But what's the signal? What's the cue that yells action and gets this whole performance started? Well, that's what we call the spark of contraction.
It all kicks off with a simple chemical signal. Calcium. See, when your brain tells a muscle to move, it releases these tiny little charged particles called calcium ions. These ions just flood the area and they bind to troponin. That's our first regulator protein. Now that binding makes the troponin change its shape, and that change pulls the other regulator, tropomyosin, right out of the way. And boom, just like that, the road is totally clear for myosin to finally do its job.
And really, this is the key moment right here. Before that calcium signal shows up, tropomyosin is literally, physically blocking the path. It's a roadblock. But as soon as that signal arrives, the roadblock gets moved, clearing the way for the myosin motor to connect and finally get to work.
Okay, so the road is clear, the signal has been given. Now we get to the main event, the engine itself. So how do these tiny little proteins actually generate the kind of force that can move our entire bodies? It's pretty amazing when you think about it.
Well, the whole secret lies in something called the cross bridge. This is the actual physical link, that moment of connection when the myosin motor grabs onto the actin road. And this isn't just some passive connection, not at all. This is the exact point where all that mechanical force is actually generated. Honestly, the best way to picture this is to imagine thousands upon thousands of tiny myosin hands, reaching out, grabbing onto the actin rope, pulling it just a tiny distance, and then letting go. Reaching out again and pulling again. It's this super rapid, repeated cycle of grabbing and pulling, that's the cross-bridge cycle, that ultimately shortens the muscle and creates movement.
So, we've seen this tiny little pull happening at the molecular level. But how in the world does that minuscule action scale up to become the kind of power we use to lift, to run, to jump? To figure that out, we're going to start zooming back out now, connecting this microscopic world to the one we actually live in.
I mean, that's a great question, isn't it? All this pulling is happening deep inside the muscle fibers. So how does that force actually get transferred to our bones to make them move? Well, it turns out there's one more key player we need to meet.
The answer is a structure called the aponeurosis. Now, it's not quite a tendon. Think of it more like a broader, flatter sheet of really tough connective tissue. You can almost see it as the bridge that gathers up all those tiny little forces generated by millions and millions of cross bridges and combines them all into one powerful pull.
And that elastic band analogy, it's perfect. The aponeurosis takes all the power that's being generated deep inside the muscle by our little protein actors, and it efficiently transmits it outward, pulling on the bone and creating the movement that we actually see and feel. It really is the final crucial link in the chain, taking us from protein all the way to power.
And there you have it, the whole story. From a sudden flood of calcium to a whole cast of proteins playing their parts perfectly, all the way to a fibrous band transmitting that power. It's like an entire microscopic orchestra working together in perfect harmony just to make you move. So, the next time you smile, maybe you'll think about that incredible, silent, molecular dance that's making it all happen.